So we've been on a bit of a journey for a little while here. So our goal today, when you're on a long hike, every now and then you come up to a sort of local maximum and you see the kind of mountain range you're trying to get to. And then of course, you're kind of tired and hungry. You see this wonderful mountain, so at least you kind of take a break and you enjoy looking at it. Then you got to get back down and climb back down before you actually get to climb it. So that's what we're going to do today. So we're going to get a first look, and the point is that it's actually possible to describe the object that we're talking about in a few lines. Okay, the actual thing that we're talking about, that's going to be the picture for this picture in the space of kinematic data that determines the amplitudes, can be extremely simply described. Understanding why this very simple, rather abstract description does the job is going to take a while. Okay, but we've motivated enough that we're going to be able to see it and talk about it. Hopefully, I'll be able to at least define things by the end of the lecture. So our goal in this lecture is to pick up from where we left off last time, which I'll review quickly, the part I said too quickly at the very end. But we're going to start talking about polytopes and cyclic polytopes, but then talk about some natural generalizations of these ideas into Grassmannians. So I'll tell you what a Grassmannian is, but the diagram that we're going to be exploring today is how we start with pictures of triangles, and we know that we can sort of glue triangles together and make interesting objects out of them, like polygons. Polygons have generalizations to higher dimensions, polyhedra, polytopes. So there's a sort of simple way of sort of thinking of going from simplices to polytopes. And there's a very special class of polytopes that's going to be relevant to us called cyclic polytopes that I'll tell you something about. But then all of these notions are generalized into the Grassmannian. And so just to say it right now, we've been working a lot in projective space. And if you remember, projective space is just a space of lines through the origin in n dimensions. But once you start thinking about that, it's very reasonable to think about the space of 2 planes, 3 planes, k-planes through the origin in n dimensions. That's the Grassmannian. Now, if you're a mathematician, you've heard of these things when you're 10 years old or something. If you're a physicist, you would naively not give a rat's ass about them. They sound like one of infinitely many things mathematicians study that you don't care about. But there's going to be some interesting, but they are very natural objects, and they're going to be important sort of nonlinear generalizations of polytopes. And the analog of the simplex in the polytope is an object called the positive Grassmannian. Okay, so now again, this is something that will be very, very simple to define, and is going to take us the better part of 2 or 3 weeks to really understand deeply and properly. It's a very rich, remarkable object. And we'll understand the way it also arises kind of surprisingly in a very direct way by thinking about scattering amplitude. So starting the next lecture, or whenever we get finished from this class, we're going to go all the way back to physics and build back up and see all these structures arise from our own natural point of view. But anyway, there are objects that live in projective space, and they have generalizations to the Grassmannian. But simplices can be generalized to polytopes, or the cyclic polytopes is the very, very special class. And the positive Grassmannian in this way is going to be generalized to the amplituhedron. And this is actually amplituhedron for tree-level amplitudes. So it's called the tree amplituhedron. I will leave the discussion of the loop amplituhedron to later lectures when we know more what we're talking about at the level of loops. OK, but yes?
Are you going to speculate on the are you going to say one of them is a replacement for space-time?
Yeah, in this very, very specific case, we've gone to the boundary, the analog of the boundary of space-time for this question, which is we've found the simplest set of variables. In this case, is the momentum twistor space. So our data is n 4 vectors. Okay, so that's it. We have n 4 vectors, one momentum twister for every particle. And so we can ask again the question I asked in the first few lectures. What the heck are we supposed to do in this space of n 4 vectors? Right? We have to find some question to ask in the space of n 4 vectors whose answer is scattering amplitudes, what we normally think of as coming from evolution in space-time and unitarity and locality and all the rest of it. So now we're just going to see, by the end of this lecture, what question you have to ask in that space. Right? So this is kind of the hologram, the like flat space hologram for this problem, at least at tree level, is there's a question you're going to ask in the space of n 4 vectors. All it's going to take is 2 words. First, the 4 vectors have to be ordered in some way. So we have that ordering in the underlying theory. It's the color ordering of the Yang-Mills scattering process. So there's a word ordering and a word positivity. Okay? So we have to say sort of 2 words, and then there's a sequence of questions that we ask in this space whose answer is going to end up giving us objects that we can identify as being local and unitary evolution in space-time. So it's not only a replacement for space-time. So if I want to say the most diminutive thing I can say about it, it's that, oh, it's very special theory, only at tree level, it's perturbative, blah, blah, blah. We can say as many diminutive things as we like about it. If I want to say the most ambitious thing about it, it's not even only space-time that we're replacing. We're replacing quantum mechanics too. There's nothing that looks like a Hilbert space. There's nothing that looks like a space-time. What we get is just some crazy, weirdo combinatorial question in this space that turns into a geometric question whose answer has all the properties that we normally ascribe to unitary local evolution in space-time, and which, by the way, describes the actual real world out there in some approximation. Okay? So it actually describes real-world gluon scattering that happens when protons hit the cosmic ray protons hit the protons in the atmosphere. That happens at the LHC all the time. So, sorry? It's a different. Not really, no. Well, but we'll see. It's not a different hologram for a different n. It's it's a different shape for different n. Just like if you have a polygon, if you have more n, if you have larger n, then there's then the polygon changes. But a polygon is a polygon is a polygon. It has a sort of uniform definition which doesn't depend on n. However, it would be very nice to find, and there's also a very specific sense in which the object for any fixed n is contained inside the object at higher and higher n. So in a sense, if you give me the object at infinite n, you're done. All the other ones are sort of in there somewhere. However, having said that, right. So actually, n is infinite. Indeed, actually, n actually is infinite because we keep emitting more and more particles because of the collinear divergences and so on. So finding some way to actually more naturally glue these different objects together into one master object is a very nice open problem. There's lots of senses in which it should be done. It has not been done. It has definitely not been done. Yeah, but well, I mean, this is this is a sort of general theme here is that a lot of people here at Harvard are thinking very hard about exactly these fascinating issues about what the singularities look like, what the collinear singularities look like, what the soft singularities look like, and all of those singularities are reflected in the objects that we're talking about, but in perturbation theory, and when you're working at the level, at tree level, there's no issue. We just have rational functions, and these rational functions, as we saw early on in the lecture, have specific kind of singularities that reflect those soft and collinear divergences. At loop level, it's a more interesting story. Those singularities are somehow reflected in some anomalous way. The symmetries are reflected in some anomalous way on the level of the actual amplitudes, and that's what begins to tell you that you should maybe not think about the object at fixed n. It's not really there at fixed n. You're actually emitting an infinite number of particles in any physical scattering process that are softer and softer or more and more collinear. But most of the geometry that I'll be talking about until the very end of the course is going to be at the level before you do loop integration. So here we haven't even talked about loop stuff, but when we talk about loop stuff, we'll be talking about what you can think of as the integrand of the amplitudes, what you get by summing all the Feynman diagrams before you did the loop integration. That has a disadvantage that it's not the physical object yet. It has the advantage that it's completely finite, no problems, totally well-defined, rational function. Okay? And so you can play, so all these physical properties that are supposed to be there are actually reflected in that object before you do the integration. So you can delay for a little while dealing with the extra subtleties. Of course, the subtleties are there, they're crucially tied into the physics, and I think it's very unlikely that the entire story is going to just have some little add-on at the end, how you deal with the collinear singularities. It's very likely a crucial part of the story, but that's something that we don't have a good picture for yet. Yes, you had a question.
No, I'm just wondering, what's the difference between tree level and loop level at this point? Because as soon as you start integrating over phase space, you get singularities at tree level too.
Well, but I'm not integrating anything. There's no reason for me to integrate anything. So I can talk about. You're right. If we do phase-space integrations, we also get singularities. But of course, phase-space integrations at tree level of amplitudes mod squared are imaginary parts of loop level amplitudes. So it's really Okay. So now, so let me very quickly recap the story just of polygons for the umpteenth time. But I want to be very clear about what we're doing. There's a few things going on, and if we understand them all in this simplest setting, then we can go to the less familiar situations a little more easily. So here, remember, our data are a bunch of external points, Zi, I1 to 3. And we had our point y as well that we care about. And let me do something that I have not been doing in the previous lectures, because everything is projective, and we're automatically drawing a two-dimensional picture associated with this. Let me just remind you that if you really think of this as a 3-vector, this was some, so we were drawing pictures like this. But this is really some line through the origin, some other line through the origin, some other line through the origin, some other line through the origin, if I think of it as a 3-vector. Okay, so it's like a cone. Okay? The whole thing is like a cone. However, when we projectivize, what we're seeing is the quadrilateral. And so y also, saying that drawing this projective picture where we say y is inside the polygon, says that y is some vector that's sort of piercing through here. Okay, so that would be y. Maybe this would be z1, z2. I mean, if I literally plonk down specific z's, there would be vectors here, but the rays are what we're supposed to care about projectively. Okay, and we talked about this object, the canonical form. And this canonical form, which depends, we began with by thinking of the function of y, and of the external data, ZA is sort of imagined fixed. So we imagine that this is a form in y space. Okay, so as we said, every form we can pull out this y d squared y, and so it's some little omega of y and z, and so we could write this as y d squared y. This is one triangulation. So there are many ways of getting this answer, but one triangulation, one natural triangulation that we talked about, that looks like the one where you anchor all the triangles to 1, was y d squared y, the sum over I, 1 I plus 1 squared over y1i, y1i plus 1. I plus 1. I'm just writing these things so we see that there are explicit formulas for it. And we found another. This is a form with logarithmic singularities. And so another way of making the fact that it has logarithmic singularities manifest is that the sum over y d log y1i over yi plus 1 d log yi1i plus 1 over yi plus 1. OK? All right, so that's our canonical form. And then we also talked yesterday about how from this differential form we extract an amplitude, or a superamplitude. And we did it, again, this is our toy model. The way we extract the superamplitude from this toy model, or at least for this toy model, is the following. I gave you two different ways. One of them is the following. So to get the amplitude, m, which depends, for our toy model now, right, which depends on the little za and the supersymmetric a to a. Okay, so how do I get that? Well, one way of getting it is the following, is we look at this function little omega. we set y to some canonical place like 0, 0, 1. I can always rotate so it's of that form. We set the ZA to be little two-dimensional ZA and have this bottom component be this Grassmann product phi I a to I, or phi a to a, where a runs from 1 to 2. And then we get rid of that phi just by integrating over it. Okay? So that was the first method that we talked about for going from this differential form to a superobject. So already this shows how this y business bosonized supersymmetry. We don't have to deal with supergeometry. We're just dealing with ordinary geometry. Okay. Now, there's a second way that we learned to, there's a second object that we thought about, very closely connected, but importantly different. So we went back to this picture, and here, let me be explicit, we think of this as a canonical form that lives on y space. So the z's are kind of dummy external data, and it's living on y space. There's a second thing we can do, which is to have a form omega that lives is only a function of the little z's, not the big z's. It's only a function of the little z's. Okay? And so this is also a 2 form. And this, a concrete formula would be just exactly this, the sum over I d log 1I over I plus 1 d log 1I plus 1 over I plus 1. But I'm just writing it explicitly just so you see that this is a 2 form that lives on little z space, not on the big z space. So these little z's are 2 vectors, not 3 vectors. OK? It's clear how we got it, right? It's closely related to the form that we had before, except that now we imagine that it's that this d hits everything, and we only keep the part where it hits the little z's. So everything else only depends on the data projected through y. Okay? Or if you just explicitly shove in that form, we'll only get these things that depend on 2 brackets. OK, now this is a more interesting form. It's just a 2 form, and it lives directly on the bosonic space of the z's. There's no y, there's no auxiliary or anything, just directly on the bosonic space of the z's. Remember, this 2-dimensional space of z's is our toy model for the 4-dimensional momentum twisters that we're going to talk about momentarily, that we care about for the amplitudes. So this is a 2 form that lives directly on the space where it's meant to live. Now, how do I get the superamplitude out of it? The good news is that it is the superamplitude directly. Okay? This form is literally equal to. So if I take this omega, and I send all the dz's, all the dzi, and I replace them with a to I, then I'll literally get the amplitude, which depends on the z's and the etas. So the superamplitude all along was a differential form. Those etas were telling us, where have we seen anti-commutative things before? They're just differential forms. Okay? So the superamplitude is literally a 2 form on the bosonic space of the on the bosonic kinematic space. Now I want to stress something very peculiar here, which is that this might bother you a little bit. It might bother you that I'm saying the dz I, this index I that runs from 1 to 2, this is supposed to be the SL2 index, right? The I index on the etas is supposed to be some completely separate. There are as many of them as each other because the theory is supersymmetric, but this is supposed to be a totally different index, which is an R-symmetry index. So when we wrote these things before, that's why I gave them different names. This is a rather peculiar thing that we're making this identification between the external conformal symmetry and the internal R-symmetry. Okay? And if I handed you some random differential form, this would not give you anything reasonable. This will turn out to be a very special differential form, a kind of weird differential form that if I ask you to write a 2 form on Z space, well, you know, there would be no problem to have expressions that involve brackets between dz1 and dz2, dz3 and z4, let's say. Okay, I could write down expressions like that. And those would mix up the indices of the z's, of the dz's and the z's. Somehow, mysteriously, the forms that we talked about always contract the dz's with the dz's and the z's with the z's. And because of that, there's sort of an emergent 2 copies of the SU2 symmetry, which is not super obvious right now. When we connect these things to the Grassmannian, all these things will become obvious. But at the moment, it's a surprise that it's an interesting form. In other words, if I give you a superamplitude, you can trivially turn it into a form. I just make all the etas dz's. In order to take a form and recognize the superamplitude, it had somehow better be that the dz's always contract with each other, and the z's always contract with each other, and that will end up being the case. OK? All right, so that's cool. There's this 2 form. We think about scattering amplitudes as a form, or this toy scattering amplitude as a form on the bosonic space of the kinematic data. But in what sense is this form associated with the geometry? So now this is the question that we want to understand in this simple setting. Because in the previous case, we thought of this form in Y space as being the canonical form for this polygon. So it was great. There's this 2-dimensional space. There's a 2 form. The 2 form has logarithmic singularities on the boundary of the space. Now we have a different situation. We have a 2 form on the space of 2 n 2-dimensional vectors. This is a very high-dimensional space. There's a 2 form. So where's the geometry? How do we see what we saw before with the polygon? OK, so in order to see it, let's go back to drawing our picture. You know, here sort of literally now I'm drawing some actual z's. And here's y. So these are my 3-dimensional vectors, z1 through zn, and y. And now what I want you to do is imagine looking at this picture in the direction of y. So in other words, project through the direction of y. Y is a vector pointing in some direction. Just point in the direction of y. Mechanically, it's exactly what we're doing before. It's like going to it's like doing an SL3 transformation to bring y to this form, and then we just pick out the top 2 components of the z's. OK? So remember, in this picture, we think of the z's as, in the normal picture, we're thinking about the z's as fixed. Imagine y is somewhere in here, and what does it look like? So what does the 2-dimensional picture of z's look like? Well, in this case, kind of looks like, it looks a lot like the projective picture we were drawing before, except it's a little bit different. This is not a projective picture. Okay, I'm literally taking this configuration of vectors and just projecting through y. If you rescaled z1, the picture would change, okay, because I'm actually literally keeping track of where the vectors are. Y has gone to the origin. So there's some origin in this space. Okay? Y has gone there. Because I projected in that direction, it's 0, 0. All right. But now I'm going to ask the question, what would this configuration of z's look like? What would it look like if I kept the z's fixed, but I just moved around in y? So let me move y around. OK, well, as I move y around, this picture is going to change, because I'm projecting through y. But it's very easy to see how it's going to change. For example, I can get to a general y. I can get to a totally general y. A totally general y would look like some 2-vector, yi here, and 1, let's say. Let me just rescale the bottom to be 1. OK, so that's the most general y that I could get as I move y around. But this is just an SL3 transformation on the original one. Okay, so I know what the new z's are going to look like. So if y looks like this, the new z's are going to look like, now my z's, I forget about all this Grassmann business. Now my z's are just za and some xa downstairs. So let me call it delta a. OK, so my za are just going to be the little za plus yi plus, so this is a za I. Let me put this index upstairs. So za I plus yi delta a. And whatever it is downstairs, I don't care. Okay, is it clear what I've done? I've done an SL2 transformation, an SL3 transformation that just which just adds y times the bottom component. If I do that on the z's, this is what I get. Okay, so if I move y around, I've moved the z's around as well. If I start with some special z's to begin with, so if these were some special z's, z star 1 through z star n to begin with, then I get a sort of family of z's in this way. All right, is this clear? Is it clear what I'm doing? I'm just sort of imagining what things look like in z space as I move y's around. Notice that what I'm accessing in this way is a two-dimensional sort of hyperplane subspace in the z space, in the space of 2 by n matrices. We're going to talk about Grassmannians in a moment, but here we're sort of seeing them without saying them. But if I imagine, so this is a loose picture, but if I imagine that here I have some z star to begin with, then I'm looking at everything I get from this z star translating in some direction delta. Okay? And this is an n-dimensional space. So if I take any one of the components, like I equals 1, right, then I have an n vector for z star, and I'm translating it in the direction of another n vector delta, a. Okay? So I've drawn it in this way, but this is, in our case, this is a two-dimensional subspace in the 2 by n dimensional space of z's. Is that clear? Okay. Notice, by the way, that this is kind of a redundant labeling, right? I could have also given you that z star, or that z star, or that z star, and they'll all give you exactly the same subspace. So I can label this subspace in a lot of different ways. The data that labels the subspace, what is the data? The subspace, so this 2D subspace, is labeled by giving me first the starting point, z star. So I can stack that into a 2 by n matrix. Here's z star 1, sorry, little z star 1, little z star n, and these deltas, delta 1 through delta n. Okay? So I can think of this as associated with some, therefore, some n three-dimensional vectors. So I'll call them z star, big z star 1 up to z star n. That's the data, and it's some fixed data to specify this fixed hyperplane. Okay? And notice precisely that the freedom to move z star in the direction of delta just means that I don't just have SL2 transformations, I have full SL3 invariance on these guys. Okay, so if I act on this z star with SL3 transformations, then I just redefine my starting point on the plane, but I get the same subspace back. Okay, so I'm doing this very simple linear algebra very slowly because it's a slightly, just a slightly unfamiliar idea, very, very slightly abstract thing that we're doing in the space of kinematical data. In this case, for our toy model, in the space of n two-dimensional vectors, there's a 2 form that lives on this space, and that 2 form, first, that 2 form is the scattering amplitude. Okay, if we just interpret the dz's as etas. But I want to find some geometry. Okay? I want to see somehow this 2 form is a canonical form for something. I want to find what before we were calling y. Now there's no more y in this picture. Okay? And now we found how to, we've seen where y is hiding. Y is hiding in this choice of these interesting two-dimensional subspaces. So if you just tell me, I'm going to look at this interesting set of two-dimensional subspaces in z space, where I start with a point z and I take off in any direction, that specifies some two-dimensional subspace, and that choice is in one-to-one correspondence with, in our previous picture, fixing some z stars as external data and moving around in y. OK. And now I can actually finish telling you what the story is that intrinsically defines what this form is directly on z space. And that's the picture that we're going to generalize for amplitudes in a second. So I told you about this subspace, but now let's actually go back and ask, what does it look like? What does this configuration of z's look like? Well, sort of here we see it kind of looks like a polygon, right? Remember, beforehand, we were saying that in the polygon picture, we had to have that all the I plus 1s were positive. So that means in this underlying picture that I have to have all the I plus 1s are positive, right? So that's perfectly fine. But that's not enough. Now I don't have y anymore. I want to say, what is special? What does it look like in z space? Well, this is what it looks like. Again, it looks like there's an origin, and all my vectors are forming a closed polygon. Here's the origin. Here is z1 up to zn. But it is not enough to say, in order to specify this picture, of course I have to say that all the zi plus 1s are positive. Okay? That just means that they're winding around in the same direction. Okay? But that's not enough, because I can do that and have a picture that looks like this for the z's. They're all just still winding around, all in the same direction, no problem. But that's not what it looks like. We never get a picture like that. Okay? When I start from these underlying z stars and I move y around, I always get something that looks like a closed polygon with winding number 1. Okay, so there's an extra topological requirement we have to put on this picture. We have to have that the zi plus 1s are bigger than 0, and that the winding number of this collection of simplices, I plus 1, so this is a very heavy-handed way of saying it, but there's a collection of intervals, 1, 2, 2, 3, 3, 4, and so on. That's topologically an S1. And its winding number around the origin has to equal 1. OK? We're not restricting kinematical data. Now I'm coming to the final story. I'm not restricting anything yet. I'm just telling you what it would look like if you had some fixed z stars and you move y around the inside of the polygon. What it would look like in the two-dimensional space is just the space of things that wind around consistently the same direction, always with winding number 1. OK, so here is the full story then. So it took a little bit of time to set up. But here's our kinematic space. So here our kinematic space is literally the space of z1s through zn, 2 by n vectors. Okay?
Why is inside inside the z space? You're only moving y inside the z.
Yes.
So this two-dimensional hyperplane you get has boundaries?
Oh no. So if I move y anywhere, I'm coming to this. Just if I move y anywhere, I have this whole infinite two-dimensional plane. If I keep y inside this subspace, then this two-dimensional plane is going to have some interesting boundaries. That's going to be where we're going to see our polygon now. Okay? But I'm trying to say it. Let me first say it abstractly. So in this big kinematical space, there's a region that we'll call, this is just some top dimensional, some chunk of the big kinematical space that we can call the positive region. P. In this case, what is this region? This is that part of big Z space for which all the I plus 1s are positive, and we have winding number 1. OK? That's an interesting part of the kinematic space. I'm not forcing the kinematics to look like that. I'm just saying in kinematic space, we're looking to find an object on kinematic space, not with fixing particular kinematic points. On kinematic space, there's this interesting part. Okay? Furthermore, in kinematic space, there is some interesting two-dimensional plane. this family of subspaces. It's not unique. You give me any z star. You give me any z star. Associated with that z star is some subspace that depends on z star. Okay? Yes?
Are you saying that there are some privilege, that you fix that star, there's some privileged plane, or is it just all planes?
All planes of that, but just choose any one of them you like. Okay? But I'm not choosing any one. I should have reminded you of something. This z star that we built, this z star that defines the hyperplane, looked exactly like our three-dimensional data in the y picture of the problem. So the z star, which was our little z star and delta, this 2 and 1 by n matrix, okay? We have to have that, I'm going to have to put some positivity condition on z star that I'll come to in a moment as well. But apart from that, yeah, there's a whole continuous family of these z stars. Choose any one you like. The claim is that this z star intersects this positive part in an interesting space. It has boundaries. That's where we discover the polygon. Okay? Notice that moving along on this subspace is exactly a function of y. It's exactly the y that we had before. That's how we see y now in this picture. Okay? Y is moving along this interesting subspace. But now I have this 2-form omega. It lives everywhere. 2-form lives everywhere. We defined it. It's the sum of d log 1i over I plus 1, etc. That 2-form lives everywhere. But it has the property that when you pull it back to this 2-dimensional subspace, so omega pulled back to S, now this is a 2-form. It was always a 2-form. It's a 2-form on the subspace. But what is this 2-form? It's the canonical form for that polygon. Okay? For the polygon that we discovered on this subspace. Okay. So the first thing is pretty. But let me summarize. So we have these 2 ways of thinking about now the forms associated with the polygon. One of them is a form on y space. This is a little more familiar, right? We would just draw a picture of a polygon. We're very happy. The z's are fixed. We're moving around with y, and this form has singularities on the boundary. Great. Okay. The only funny thing about it is that we don't see y in the problem to begin with. We don't see these extra components in z to begin with, and so on. Okay, so but that's fine. We found this rule for associating the superamplitude with these objects anyway. Perfectly fine picture, but there's this equivalent picture which is a little more abstract but quite a bit deeper. Okay, which is that we think about things directly on the space of the kinematical data. Nothing going on. There's no y. There's no extra components. There's no supersymmetry. Okay? There's just this interesting space. In the space of kinematical data, there's an interesting part. There's an interesting part where what the kinematical data look like is that they're winding around the origin with winding number 1. Okay? They're winding in the same direction around the origin with the whole thing having winding number 1. And there's a linear subspace in the kinematical space, which is 2-dimensional. And the intersection of that winding number 1 region with this 2-plane actually looks like a polygon. The shape of the polygon depends on exactly which subspace you chose, but you chose any subspace you want. First, geometrically, the intersection of this plane with the subspace looks like a polygon. And now you can ask, is there a form in the world? Is there a 2-form in the world that has the property that if I pull it back to one of these subspaces, whichever subspace I choose, it's always the canonical form for that polygon? And the answer is yes, and it's the amplitude. It's the superamplitude directly. It's the form that we interpret as the superamplitude. Okay? All right, so this is probably a little much to swallow in one go, but we'll be coming back to this. Picture a number of times. And as we go, I'm going to develop both this sort of y picture as well as this more intrinsic Z picture. And they're closely related to each other. The Y picture tends to be a little easier to visualize and think about. But as I said, this is closest to what we want. It's sort of a hologram directly in the space where the objects live. Well, so in about a month we'll be seeing. It's kind of ironic because in many ways there's a much simpler story that I could tell about phi cube theory, where we don't have to see quite as many geometric shenanigans. But for a variety of reasons, I prefer doing it this way first. But yes, we'll be seeing exactly the same, literally the same picture, okay, for phi cube theory, theories of Higgs scattering, okay? Everything is the same, just what is this kinematic space is different. We work in the space of Mandelstam invariants instead of momentum twisters. What the positive part is different, what the subspace is different, but this idea that the amplitude is a form, there's a positive part, there's a subspace, and you pull back and you find a positive geometry on that part, and the amplitude of the canonical form is the same. And there's a picture like that for, that's being developed for cosmological correlators as well. Exactly the same. Completely exactly the same. There's a kinematical space, subspace, pull back, canonical form gives you the physical observable. Okay, so, okay. All right, so now in the rest of this lecture, so that's all we're going to say about polygons. Okay, so just saying it very quickly again, we talked just about areas of polygons, but we've then quickly transitioned to talking about these canonical forms instead. So canonical forms of polygons are related to the area of the dual of the polygon, but now we've been playing with these forms instead. These forms we can think of in these two different ways. In Y space, most directly, most obviously, most intuitively, and we'll develop that more, but also in the slightly more interesting way, directly as forms on the ultimate kinematical space that we're interested in. So now what we're going to do is generalize all of these things beyond polygons, first of all. So we'll first talk about polytopes in higher dimensions, and then the more interesting or the sort of newer generalization, not more interesting, but just newer generalization into Grassmannians that I'll define and talk about. All right. So now let's talk about, first in general, about projective polytopes. And to begin with, we've said this, we've been drawing these pictures a few times, but we've not written down this formula yet. Let's say you have a two-dimensional picture, nothing fancy going on. These are just ordinary two-dimensional vectors. I'll convince you that they're ordinary by putting a vector sign over them even. I'm not proud. Okay, so they're ordinary two-dimensional vectors. And I'm interested in points inside this triangle. So how do I think about points inside that triangle? Well, every point inside the triangle, I can think of it as a center of mass idea, some weighted sum of x1, x2, and x3. Okay, so what are all the points inside? Look like y equals, m1. Let me call it. I'll be calling them c's for a variety of reasons. c1x1 plus c2x2 plus c3x3 over c1 plus c2 plus c3. And it's very important here that all these c's are positive. So all the weights are positive, and so every point on the inside of the polygon is of the triangle is of this form. Now, if I want to talk about the point on the inside of a polygon, it's the same formula. It's just y is equal to c1 x1 plus dot dot plus cn xn over c1 plus cn, and all the c's are also positive. And note something very important about this case. It's not true for the case of the triangle, is that in the case of the triangle, the c's are basically fixed up to overall scale. Okay? But a point inside can uniquely be written as a linear combination of the points on the corners. That's not true here. Okay? That is not true here. I can have lots of different masses. Obviously, there's many, many more parameters there than there are parameters describing two-dimensional space of points inside this polygon. Okay, but now this definition clearly generalizes to any number of dimensions. And this gives us our first example, our first definition of a polytope. So if you give me a collection of vectors vi, some collection of vectors v1 through vn, then I look at all the points y of the form c1 v1 plus cn vn over c1 plus dot 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 cn, and we call this the polytope, which is a convex hull of these vectors v1 through vn. Okay, so that's just a definition. The word convex hull just means you're taking a positive weighted sum of all the vectors. Okay, and once again, this is a highly non-unique. This is a highly non-unique map. Okay, so I have to scan over all the positive c's I can, and the space of all the y's that I get in that way is the interior of the polytope. So we can draw obvious three-dimensional pictures, but I don't think we need to. Now, here's a more interesting point, which is that, as I've stressed many, many times, whenever you're doing anything in geometry where there's no notion of a metric, it's better to think about it projectively. And it's also better to think about it projectively here. So in order to think about this projectively, we'll just go up one in dimension, right? We'll add 1 to everybody. So I will work, for example, back in this picture, I will have some variables za, which are those two vectors xa, let's say, right? No problem doing that. And now you see the formula for y is much nicer. The formula for y, so this is some zai that now runs from 1 to 3, right? So the formula for yi is just c1 z1 plus cn zn. Now I don't have to divide by c1 plus c2 plus up to cn anymore, right? Because the top component of this formula will be c1 plus c2 plus cn for y. And so projectively, it's the same when I go back to rescaling y to 1 to dividing by c1 through cn. So this is a much prettier formula. OK? So if you're given any, and so another way of saying this is that I'm going from a picture, ordinary picture of a square in the plane, to a cone. Just like I'm sort of going backwards from the pictures that we've been drawing intuitively already, where we have been making a big deal about it, but just saying a little bit more formally. Okay? So the space of all y's is the interior of that cone. All right? And again, we can now we can think about this projectively and get many different pictures of the polytope that we have to begin with. Now, we can slice with a plane at infinity and get back literally this picture, or we can move the plane at infinity around and get many other pictures that are related to this one by SL3 transformations. Okay? So, all right. Now, it's important to stress that you can't go backwards always, right? So, if I gave you some collection of vectors, xa, I could build these z's by putting a 1 upstairs, and then this formula is great. Okay? That formula is perfectly fine, but I can't necessarily go backwards. I can't, it's not necessarily true that if you give me a whole bunch of z's, that I can just willy-nilly write down that formula c1 z1 plus cn zn and have it make sense and correspond to a polytope. Why not? So let's just look at the simplest example, and we'll say it sort of obviously, intuitively, and also formally. So here is an example of a good configuration. So here is z1, z2, z3, z4. Let's say just in the plane. OK? What is c1, z1 plus c2, z2 plus c3, z3 plus c4, z4? It's just the inside of this triangle. No problem, right? So that's a perfectly nice space. It's a cone. And if I intersect it with a line to choose a plane at infinity, a line infinity, I get an interval. Okay, so that's the geometry that we're talking about. So this case is good. So the case where my vectors look like this is good. Here's a bad case. This is bad, right? Because now if I take the combination of all these guys, it just covers the whole plane. Okay? So in order for this formula to make sense, it has to be something that we just did tacitly here, putting a 1 on top for everybody. It must be that all these vectors, z, are on the same side of some hyperplane. Okay? Otherwise, it doesn't make sense. They all have to be on the same side of some hyperplane, which I can choose to be the plane of infinity if I like, but it doesn't matter, right? They have to be on the same side of some hyperplane, and then this formula makes sense. Let me say this slightly more formally. You see, I want this formula, y equals c1 z1 plus z1 plus cn zn. I sometimes forget that I'm Canadian. Okay, so I want this formula to make sense of the formula in projective space, in the projective space of P2. But remember, the point 0, 0, 0 is not in the projective space. So in order for this formula to make sense, it had better be that the left-hand side can never go to 0. Okay? Now, if you have a triangle, if you have 3 points, it's no problem. It can never go to 0. But beginning with 4 points, it could easily go to 0. After all, you know, Z4, it could be a linear combination of Z1, Z2, and Z3, and so it could easily go to 0. So you need something special in order to make sure the left-hand side can't go to 0. And that's something special. Just obviously, they all have to, there has to be some basis in which it's impossible for them to go to 0 because the top component of all of them is 1. Okay, so they're all on the same side of some hyperplane. Okay, is that clear? But in this way now, provided that is the case, we have this sort of nicer projective way of thinking about what polytopes are. Okay, so you can think of them equivalently as this cone, but I prefer to think about them as polytopes, but thought of projectively, projective polytopes. Okay. All right, but now comes a natural question. What does this polytope look like? Right? So in the case of the polygon, every polytope in 2 dimensions looks like a convex polygon. They all look the same. But you already know, starting in 3 dimensions, you get all sorts of cool shapes, all sorts of polyhedra of different shapes. So what does it look like?
Sorry, question.
Yeah.
So in this homogeneous coordinate, I should think of the lines to the origin, right? They
Yes.
don't have an origin. They don't necessarily have a...
Thank you, thank you, thank you. So that was just the a point I just forgot to make. I was going to make. You see, once we find that they're all on the same side of a hyperplane, so they're sort of pointed like this. Now, and this is very important because we're going to be talking about the notion of positivity a lot. And I snuck this in the last couple of lectures, and nobody complained, but somebody could have complained, and then I would have told them they had to wait a couple of lectures. Okay, okay. Now we're going to talk about a slightly restricted notion of projectivity. Okay, we're going to ask. See, now I don't care about the other rays anymore. I don't care about the rays on the other side anymore. They're all in one direction, right? So I'm just going to look at the half of the space that's on the right side of the hyperplane that we care about. And so, very important, is that now we're going to imagine rescalings like ZA goes to TA ZA with TA positive. Okay? All right, and similarly for Y. And everything that we're doing projectively has some positivity even in the rescalings that we're talking about. This is because everything is sort of pointed and we're living inside this cone. Right? Otherwise, that formula would be complete bullshit. Right? Because I could say C1 Z1 plus Cn Zn. What the hell are you talking about? Even the signs of the C's are meaningless because I can rescale the Z's. Okay? But no, it's because it's pointed, we only keep the positive rescalings.
So given some kinematic data, you could first choose the signs for all of them to line up in the same hyperplane?
If it's possible. It might not even be possible. It could be such a complicated picture you might not even be able to do it. But yes, if it's possible, choose them to line the same side of hyperplane, and then off we go. All right. OK, so let's actually return to this question, even for polygons, again, where everything is familiar. I've given you this convex hull definition, but this convex hull definition is not sort of super useful for answering the following question. Let's say I hand you some point y, here, 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 but I'm blind. Okay, I just hand you, I can't see anything. You just give me all the coordinates of the z's, 1, 3, -7, blah, blah. Give me all the coordinates of the z, give me the coordinates of the y. How am I supposed to know whether y is inside or outside? I can't plot it, right? Well, there's a second definition of what a polytope is, which is sort of obvious from here as well. It's cut out by a bunch of inequalities, linear inequalities. So you say you're on the same side of this plane, of this line, of this line, of this line, and so on. OK? So here you're giving a bunch of facets. In this picture, I'm giving you a bunch of vertices, or a bunch of points whose convex hull gives me the object. By the way, some of those vectors might be inside, in which case they're not relevant. You know, we'll end up being the convex hull of a bunch of vertices, right? From now on, essentially all the time, in this convex hull definition, the objects we see will end up being vertices. So you don't have to worry about this. But it's nothing per se to worry about. They're not all guaranteed to be vertices. There's a second way of thinking about it, so I specify its facets. Okay? Now, if we think about this duality we've been doing all the time, this is totally reasonable that if I specify the vertices of the polytope and specifying the facets of the dual, if I'm specifying the facets of the polytope and specifying the vertices of the dual. So there should always be these two dual ways of doing things, involving vertices and facets. In this case, what is the rule for the facets? I just have to say that these brackets y1, 2 are positive, y2, 3 is positive, and so on, right? yn1 is positive. And now this is something that the blind person could check just by computing a bunch of determinants, right? So you can check whether you're inside the polytope if you're on the right side of all of these inequalities. And I'll just state something that should be quite intuitive. I won't give any real proofs here, but in general, the shape of the polytope, what I mean is what's the facet structure? What are the faces? What are the edges? How do they meet? And so on, all the way down. But the shape is actually specified by giving the following data in terms of the underlying z's. So this is a second definition. Okay? This is a second definition if we manage to find what the faces are. Okay, now moving on to the topic of what different shapes polytopes could have. And the shape is specified just by giving the following information. The collection, if you give me the convex hull definition to begin with. So I give you a bunch of vectors. So y was c1 v1 plus cn vn. OK? What you want to do is say which subset of those vectors might actually be a facet of the polytope. That's what you're trying to figure out, right? So for example, here are the subsets that were facets were like 1, 2, 2, 3, 3, 4, and so on. Okay? The fact that there are subsets meant that if I say it was 1, 2, then all the other vertices were on the same side of 1, 2. So 1, 2, 3 was positive, 1, 2, 4 was positive, 1, 2, 5 is positive, and so on. So that's the super systematic way you could figure out what all the facets are. You could say, let me see, is VA1 through VA, if I have an n-dimensional space, I want to see, is VA1 through VAn a facet? Is it a facet? And the answer is, well, if this bracket, VA1, VAn, VB, has the same sign for all B, is either 0 or the same sign for all B, then I'm done. That is a facet. OK? So this is a kind of a brutal procedure if you have a large number of points, but you can give it to Mathematica. No problem, right? I give you a huge number of vertices. You just make this big stack. You check whether every conceivable set is a facet. By the way, maybe some facet has 4 points on it, in which case you would label the same facet in 2 ways. You would discover, one triangle in the facet, another triangle in the facet, and you would discover that it looked like a square because in one of those brackets you'd get 0, right? So you'd find that a 4th point is actually on the facet. That's what the zeros are about. OK? So that should be enough to convince you, I hope, that the shape of the polytope, what the facets are, and actually everything beyond that, is determined by giving the following data, something that's called an oriented matroid. I will never use this word again. I don't really know what it means other than this definition, which is just this collection of all of the VA1 through VAn+1, all of these guys, but just whether they're +1, whether they're positive, 0, or negative. Just the signs of all of these determinants. Okay, the signs of all these, we'll be shortly calling them minors, because we're going to be stacking these vectors into matrices. So I'm going to slip back and forth into this terminology a lot. The sign of all these determinants made out of the vertices, the sign of all the minors, is all the information you need in order to decide the shape of the polytope. So let's go back and figure out what is the oriented matroid of a polygon. Okay? What is the oriented matroid of a polygon? Well, this is pretty easy to see what it is. So what do I know about the signs of ZA, ZB, ZC? I have to tell you something about the signs of ZA, ZB, ZC. And it's simply that that sign is nothing other than the orientation of the triangle in the picture, ABC. So when I order the z's in the way that's so natural and obvious, if you can see, okay, when I order the z's in this way, then the statement is simply that this minor ZA, ZB, ZC is positive if A is less than B is less than C. That says the triangle 1, 2, 3 is oriented in the same way as the triangle 1, 2, 4 is oriented the same way as the triangle 1, 8, 9. All of them are oriented around the same way. It's very easy to draw a picture where the orientations are all screwed up. Okay? But this is what I get. And everything, yeah. So this is the oriented matroid for a polygon. Okay? It's just saying that all these 3×3 determinants made out of the z's are positive. So this is our first explicit encounter with some interesting statement involving positivity of determinants. In fact, if I stack the matrices together, Z1 through Zn, if I stack these things, Z1 through Zn into a 3×n matrix, another way of saying it is that simply that all the ordered maximal minors, 3×3 minors, are positive. Okay? All right, any questions about this? Yes?
Is this the same as the previous, that they're opposite?
Nope. No, that's a much more primitive statement, that there exists some plane that separates them all from everything else. Okay?
Can we forget about winding number 1?
In this picture, we're not. In this picture, these are three-dimensional z's. So we're in the world of y. Okay, so now we haven't talked about y yet, but this is back in the picture where there's a bunch of z's and there's a y moving around and so on. Okay, so for the moment, we can go back to the picture. Yeah, there's no winding or anything here, right? We just say we have z's, they're positive, and we're done. Then that forces it to look like this. Exactly. Okay, exactly. All right. Okay, so we can summarize that, and so, you know, there's all kinds of higher dimensional polytopes. They have all kinds of different shapes, and they have therefore all kinds of different oriented matroids. But we're going to now pick a very special kind of polytope. So if I say again, polygons look like this, where the C's are positive, the CA are positive, and also the Z's are positive in the sense that all of these ordered minors are positive. Okay, so the first generalization that we're going to talk about is to Z's that are higher dimensional. Okay, so if Z's are higher dimensional, we want to find some analog of this polygon. And the aspect that we want to preserve is that there was an ordering to the vertices. As we said this a few times, if you draw me a dodecahedron, I don't know how to order the vertices. You know, I can draw them willy-nilly this way, that way. There's no obvious way to order the vertices. So I want a polytope which naturally comes with an ordering for its vertices. So all we're going to do is just copy this definition and just go to higher dimensions, right? So we'll just want to say now I is going to run from 1 to some n plus 1 for an n-dimensional or an m-dimensional, or let me say 0 to m for an m-dimensional polytope. So this is again going to be C1 Z1 plus Cn Zn. And now I'll have ZA1 up to ZA m plus 1 should be positive when A1 is less than Am plus 1. So that's my definition of positivity for the external data here. Okay, so now I have an m plus 1 by n matrix where all the minors are positive. And that's my external data. And then the convex hull of all of those guys is an interesting polytope. Okay, that polytope is known as a cyclic polytope in general. So the polygon is the simplest example of a cyclic polytope. For m equals 2, but we have general m-dimensional cyclic polytopes. By the way, we've also seen just in this definition something else that's going to be a big object of study for us for a while. So again, let me stress, now I have this m, or in general, I have some, I was calling it, let me not mix it, let me just leave it in the notation I have for the moment. I have some m plus 1 by n matrix with all positive minors. And this we'll interpret in a different way in a moment as having something to do with the space of m plus 1 planes and n dimensions. But just to give it the word now, this is the positive Grassmannian. So you see, even the interior of a polytope is of a polygon is a slightly interesting object, which is jamming together two different notions of positivity. On the one hand, I want these weights to be positive, in just a sort of like dumbest sense, that the numbers are numerically positive. Okay. On the other hand, and I'm moving those C's around. So I'm moving the C's around, and thus covering the interior of the polygon. On the other hand, I want to keep this external data can't be random. It has to have this interesting nonlinear constraint on it that all these minors, these ordered minors, are positive. So even the interior of a polygon is this interesting jamming together of two kinds of positivity, on the C's and on the Z's. Okay, we're going to generalize this in a moment, but we're actually going to start off just exploring this now because there's something already interesting here. Yes?
Just about this definition of cyclic polytope.
Yeah.
An example of a polyhedron which is convex, but it's easy to see why it can't be cyclic, like there's no ordering of the vertices.
A cube.
A cube, okay. It's easy to see.
Yeah, try it. Yeah. So yeah. I'll tell you some special things about cyclic polytopes in a second. But the first thing I want to do is figure out what is the boundary, what's the facet definition of the cyclic polytope. What do the faces look like? What does it look like, right? And now, see, we can play with the m equals 3 case, so I have some idea what it looks like. But in general, we're not going to be able to visualize things. So it's important to be able to do some of these things algebraically, right? So, so how should we decide what the boundaries look like? Remember what we're supposed to do. We want to see so let's go back to the case of the polygon, actually. How can we know? I want to know, is VA, VB a facet? And so in order to do that, I have to look at these minors, VA, VB, V1, VA, VB, V2, and so on. Or sorry, I'm using Z. ZA, ZB. So I have to look at ZA, ZB, Z1, ZA, ZB, Z2, and they all have to have the same sign. Okay, they all have to have the same sign. Okay, well, there's some hope here, because after all the ZA, ZB, ZCs are positive if they're ordered properly. So this has a chance to work. But it's not guaranteed to work because they have to occur in order here. Remember these determinants are antisymmetric, so they have to occur in order. So let's see how it works. So this is now index space. Okay, so this is 1, 2, 3. And so here's A somewhere, and here's B somewhere. I want to see, can it be that these all have the same sign? Okay, well, let's start. 1AB, oh, good, that's already positive, right? 2AB is positive, 3AB, that's great. Everything is great until I get to some guy in here. If there's any index that's stuck between them, then that guy will be negative. Okay, so therefore, AB cannot be a facet unless there's nothing stuck between them. So that's why it has to look like I plus 1. Okay, so this is how, again, our friend the blind person, without looking, could conclude that the facets of the polygon are I plus 1. Now let's do it for the cyclic polytope. And I'll leave you to do it for the odd M case. I'm going to jump to the even M case. So let's do it in the next case, M equals 4. Okay, so now we can't visualize anything. But now I want to see, is ZA, ZB, ZC, ZD a facet? So it's exactly the same thing. I have to look at this I have to look at the A, B, C, D1, A, B, C, D, N. They all have to have the same sign. And is that possible? Well, let's go back to our index space picture.
Wait, wasn't M plus 1 dimensional?
Sorry?
Wasn't M plus 1 the dimensionality of space?
No, it's an M plus 1 dimensional polytope, and therefore the vectors, it's an M dimensional polytope, and therefore the vectors projectively are M plus 1 dimensional. Just like our polygon was 2 dimensional, but the vectors were 3 dimensional. Okay, so this is the 5 bracket, right? So the z's are 5 dimensional, the polytope is 4 dimensional. All right, so let's go back to this picture. Now I have some A, B, C, and D. I have exactly the same problem, right? If there's any gaps between these guys, I'm dead. So what does it have to look like? It has to look like I plus 1, J plus 1. Okay? And now you see, no matter where you go, it's positive, 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 0. That's OK, 0. Now back on this side, it's positive again, because I have to hop through 2 things to put it back in correct ordering. So positive, 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 0, 0. And then back on this end, it's also OK, because I have to pop over 2 things to put it back in order. Right? Now, I want to pause here to make a huge deal about this. Okay? Because remember, one of the absolutely most 0th order things when we went to think about the external data, now in momentum twister space, now this is M equals 4, this is the actual problem we care about for amplitudes, is we have all these momentum twisters, and yet somehow, for some reason, whatever the object is we care about has got the care to group them together into II plus 1 and JJ plus 1 that we call points in space-time. And it has to care whether II plus 1, JJ plus 1 goes to 0 or not, because that's when those points are null separated, which has to do with factorization and all of the rest of that, right? That's space-time and factorization. And it's emerged out of nothing, out of the Platonic ether, right? We're just asking about polytopes, generalizing polygons, asking for positivity. We put nothing about this II plus 1, JJ plus 1 structure in by hand. And yet here it is. Okay? So the boundaries of the cyclic polytope, so if I summarize, the boundaries of the polygon are I plus 1, and a triangulation of the polygon is, for example, the sum of these simplices 1 I plus 1. And as we've checked a number of times, that's the correct triangulation because the boundary of that sum is exactly the sum of I plus 1. The boundaries of the m equals 4 cyclic polytope are the sum over I plus 1 jj plus 1, and therefore a triangulation of the cyclic polytope by exactly the same logic as the sum over I and j of these simplices, 1 I plus 1 jj plus 1. That, as we saw a number of times ago, was exactly the BCFW formula for these amplitudes. Okay, and now, if we ask that if I now say that y, I write the canonical form associated with that cyclic polytope, then first of all, in the first way of doing things, I can take that y, I can put it to 0, 0, 0, 0, 1. I can put the z's to 4 dimensions and a phi dot eta downstairs and integrate over the phi's, and I get the super amplitude. Okay? Now, in the second way of thinking about things, it's also cool, right? It's a little cooler again. In the second way of thinking about things, my space is n4 vectors. Once again, in this boring space of n4 vectors, there is now a part. What is the positive part? There's an origin in this space. And now I have to give you something. It's got to be some notion of winding, right? But how do I build something? How do I build an S1 here? There didn't seem to be any S1 that I can build. In 2 dimensions, there was this natural S1. We did it without thinking. 1, 2, 2, 3, 3, 4, and so on. Now, there's not an S1, but I can build an S3, something that's topologically an S3. I just take the union of all of these simplices, I plus 1, jj plus 1, right? That's an S3, and that's an S3 that has winding number 1 around the origin. Okay, so that's our positive part. That's essentially the only cyclically invariant S3 that I can build out of this data. So that's another way I would discover I plus 1, jj plus 1. The only way I can make a closed sphere out of this data in a way that's invariant under cyclic shifts. Okay. Okay. So I take that, and it has to have winding number 1. Now I do exactly the same thing. There's a 4 form that lives on this space. There is a 4-dimensional plane. That 4-dimensional plane intersects this region where the I plus 1, jj plus 1s have winding number 1 in a shape, which is a cyclic polytope. And this 4 form that lives everywhere in the whole big space pulls back to that subspace to be the canonical form for that polytope. And that form is the super amplitude directly. Okay? All right. So we've now seen everything we're going to see in the world of polytopes. Next time, I'll come back and tell you a little bit more about Grassmannians and the positive Grassmannian. I actually didn't finish. We didn't finish seeing the mountain in the distance yet, so we'll talk a little bit more about the mountain next time. But then we'll descend very quickly into the valley and spend some time learning about the positive Grassmannian. Thanks a lot.